Hey guys, Jake here coming at you with another math lesson today. Another Monday evening, 5 o'clock Pacific time, coming at you live every Monday night. Tonight we're going to be talking about separable differential equations. And, not only just separable differential equation examples, but I'm going to take a little bit of time before we jump into some examples to just talk about the steps that you go through in a separable differential equation problem. So like I said, we do have some examples that we will get into in a bit, but let's start with the steps. I've been doing a handful of videos recently where, I just talk about the steps that you would go through to solve a specific kind of problem. And I think they've been very helpful. So I want to kind of keep going down that route. Obviously not every problem that you're going to run into in calculus or, in math in general, not every problem is going to be solvable just by saying, here's a list of steps that you're going to go through. Now go through them for any example. But there are specific types of problems that definitely can kind of work out that way. Now, something to kind of keep in mind, and this is the case for separable differential equations, which we'll be going over in this video, but also the other videos that I've made recently, where I say, here's the steps you go through to solve this type of problem. Those don't necessarily work for 100% of the problems you're going to run into. They are kind of better thought of as general guidelines. I will say generally in a kind of standard calculus 1 class or differential calculus class, or in this case with differential equations, an integral calculus class, Calc 2. In kind of a standard calculus class, these steps that I've listed in these different videos probably will cover all the problems that you'll be expected to solve in those classes. But obviously kind of the idea with math is, getting a more general understanding and thinking about how we could apply this kind of general blueprint, these general steps, if things don't work out exactly the way we are used to them working out. So I think these steps videos are a good kind of jumping off point, a good starting spot. But if you run into roadblocks where these steps don't work or something like that, obviously you may have to kind of think on your toes and do something a little bit differently. But either way, I do think having this kind of general outline of steps is going to be helpful for you because, it probably will work for most of the problems you're going to run into. And if not, it should kind of get you used to what things to think about in each of those steps that may indicate that it will or won't work that way. But let's go ahead and jump into the actual steps of a separable differential equation example. So like I said, we're going to be talking about separable differential equations and the steps to solve them. So the first thing you want to think about when you're looking at a separable differential equation example, typically the problem is not going to say solve the separable differential equation. They're not necessarily going to tell you, and of course this does sometimes happen. I don't ever, like to say that this never happens, but sometimes they will tell you this is a separable differential equation, solve it, but not always. So the first question you need to ask is this a separable differential equation? Typically, a differential equation problem, they're just going to give you, excuse me, they're just going to give you a differential equation, which really is just any equation that relates x, y, and dy dx. Now, of course, the letters could change. It could be something like x, t, and dx dt, right? It doesn't really matter what the letters are. The point is it's going to be two variables and then the derivative of one of your variables with respect to the other variable. So you're kind of going to get this situation where you have these three different letters. One's a function, one's a variable, and then your d something, dy dx, or dx dt is just going to represent the derivative of your function with respect to your variable. Okay, so that an equation that contains those three things is considered a differential equation. So what makes a differential equation a separable differential equation? Well, it's pretty simple. Basically, it needs to be in one of two forms, either as it's given, or you need to be able to algebraically kind of manipulate your differential equation to get it into one of these two forms. So let's say that we are dealing with a differential equation using x, y, and dy dx. There's two forms that we could have our differential equation be. One is that we would essentially be able to separate out our equation. It depends on if you have x's on the left side of your equation, y's on the right side, or if they're all mixed together or what. But what you should be able to do is either divide or multiply anything from the left-hand side of your equation to the right-hand side, or vice versa, in order to get it into one of these two forms. And the forms are, you would either have dy dx equals some function of x times some function of y, or the other form that it could be in is you would be able to get it into the form dy dx equals some function of x over some function of y. So like I said, it may not be given in this form. We may have, I don't know, some sort of a situation where maybe we have x's and y's all mixed together on one side of our equation. So maybe we have dy dx equals something with x's and y's in it over here, but maybe we can factor this out to get us into one of these two forms. Or maybe we have some y's over here and some dy dx's, and we can kind of move things back and forth between the left and the right of the equation to kind of get it into one of these forms. Okay, so the point is we need to be able to manipulate whatever equation we're given to get it into one of these two forms. Once we know that we can do that, or if the equation is given already in one of these two forms, then we know that we have a separable differential equation. So from there, so the first step, like I said, is you would want to get it into one of these two forms. Okay, once you've gotten it into one of these two forms, the next step is to separate your x terms on one side of your equation and your y terms over to the other side of the equation. So depending on which of these two forms you got to, the way that will work will be a little bit different. If you have form number one, your next step at this point is going to be simply to divide both sides of your equation by this g of y. So you divide both sides by g of y, or in other words, multiply by 1 over g of y. That probably would be the better way to write this. Okay, and doing that will cancel your g of y over on the right side of the equation. And then what you can also do is multiply both sides of your equation by dx. So I know that probably seems kind of weird. Dx isn't necessarily typically a term that you would like multiply over to the equation like that. But with differential equations, especially separable differential equations, you can think of the dx and the dy as their own terms, basically. So basically that'll cancel the dx on the left side of our equation and move it over to the right. So essentially, once we do that, all we would end up with is moving all of our y's from the right side of our equation over to the left, moving our x from the left side of the equation over to the right, and we would just end up with g of y times dy equals f of x times dx. So this is why it's called a separable differential equation, because we can separate the x's and the y's. We can separate the letters that represent our variable from the letter that represents our function. In this case, it's x and y, but like I said before, it could be x and t or whatever else. The actual letters don't really matter, but the idea is that we can separate them, okay? If we had it in this form, similarly, we would be able to multiply by g of y to move that over to the left side, multiply by dx to be able to move that over to the right side, of course, whatever you do to one side, you do to the other side as well. So we would multiply our gy to the left side, giving us g of y dy equals, oh, wait a second. I did this first one wrong. I'm sorry. This should be, remember, we wanted to multiply by 1 over g of y in this first example here. So 1 over g of y would be multiplied to the left side of the equation. In this case, we have, in the first example, we have 1 over g of y, and then in the second one, we have g of y times dy. And then similarly, multiply the dx over, just leaves us with f of x dx. So basically, we either get it to 1 over g of y dy or g of y dy equals f of x dx. Okay. So then from there, once we have separated out our variables, regardless of which of these two forms you have, the next step is going to be the same. We basically would just add an integral onto both sides of our equation, which means that we're going to be left with either 1 over g of y dy equals the integral of f of x dx. And if we had this one down here instead, we'd have the integral of g of y dy equals the integral of f of x dx. Okay, so once you've thrown on your integral sign, since you've done it to one side of the equation, or since you've done the same thing to both sides of the equation, we haven't changed the fact that these two things are equal. Then from here, you would just integrate. So then your next step is to integrate both sides. And then once you've actually taken the integral of both sides of your equation, then you would isolate y. Or in other words, solve for y. So then after this point, you should just have y equals some function of x. And then if you were also given an initial condition to deal with, you would solve for your unknown constant that was introduced in this step right here. So when you integrate both sides of your equation, you should have a plus c, that you would introduce through integrating. And then if you have an initial condition, you would solve for your constant. Usually C, but could be really whatever letter you decide you like. So yeah, that's it. There's basically just going to be these 6 or 5 steps, depending on if you have an initial condition or not. If you do not have an initial condition, you would be done after this step, and you would have a plus C somewhere in your answer. If you were given an initial condition, you have to solve for that plus C and figure out what it actually is. So basically, this kind of 5-step process is all it would really take to solve any separable differential equation. One quick point I want to bring up on that. If you are given your differential equation already in one of these two forms from this first step here, then you don't have to do anything for this first step. You already basically are there. So if you're given something that looks like one of these two things here, then you can skip on to the second step right away. So just something to kind of keep in mind there. But yeah, you can basically use this kind of blueprint to solve any separable differential equation that you're going to run into. So now let's go ahead and jump into some examples of actually applying these steps. As always, if you do have any questions along the way in these live streams, feel free to throw those questions in the live chat. And I'd be happy to help answer them however I can, if at all possible. And if you are getting some value out of this video so far, do me a favor and go hit that like button down below. Helps get this video out to more people and helps my channel grow so I can keep making more videos like this. All right. So now that we've gone over the steps of how to solve a separable differential equation, let's go ahead and talk about an example. So this first example here, this example does not have an initial condition. So that's something to point out here. Referring back to those steps that we just discussed, the final step is not going to apply because we do not have an initial condition. I do have another example coming up here shortly, which we will get into an initial condition, so you can see one of each, see how those work. So, separable differential equation. Obviously, like I said before, the problem doesn't necessarily tell you that it's a separable differential equation. You have to make that determination for yourself based on whether you can get it into one of the two forms that we discussed. In this case, we are given something that is in the form of dy dx equals some function of x times some function of y. Right? So basically we have some function of x times some function of y. In other words, we should be able to just factor this out into something with x's in it times something with y's in it. In this case, that's exactly what we have. So we actually don't have to do any work for the first step of solving a separable differential equation to get it into the necessary form that we need, because the problem gave us something already in the right form. So we already know that this is going to be a separable differential equation because it's already given to us in the form that we want it to be. Actually, I'm going to leave this here, sorry. Okay, so since it's already in the right form, what we can do is start separating out our variables, which means we're going to move all of our x terms over to the right, all of our y terms over to the left. So basically we would multiply both sides by dx, and then we would multiply both sides by 1 over y squared, because that's going to cancel the dx's on the left. It's going to cancel the 1 over y squared with the y squared on the right. So we're just going to be left with 1 over y squared times dy equals x times dx on the right. So now we have separated our variables. We've gotten all of our y's onto the left side of the equation, all of our x's over onto the right side of the equation. So once we've done that, what we can do is put the integral sign. That was a sloppy integral sign. Let me try that again. All right, there we go. Put the integral sign on both sides of the equation. So you do need to make sure that you're doing that on both sides. Whatever we do to one side of the equation, we always have to do to the other side of the equation. Okay. Once we have done that, what we can do is just integrate both sides of our equation. So looking at this left side here, we have a dy, which indicates to us that we need to integrate this function with respect to y. We want to treat y as our variable for now, just in this integration step. The dy and the dx are basically just indicators telling us what variable we're integrating with respect to. So this is exactly why we wanted to be able to separate our y's and our x's, because now we have a situation where we're integrating the left side of our equation with respect to y, because we have this dy indicator over here, and the function that we're integrating only has y's in it. So that's super convenient. We're basically treating y as a variable in this case because of that dy, and since there's no other letters besides y, we should be able to integrate this exactly how we would hope to be able to integrate it, just using standard integration techniques. We don't have to worry about treating y as a function because we have a dy here that's telling us to integrate with respect to y. So what we can do is rewrite this actually. Instead of saying 1 over y squared, what I'm going to integrate is y to the negative 2, because y to the negative 2 is exactly the same as 1 over y squared, but it's in a form where we can integrate it just using the power rule. Okay, so the power rule for integration says that we're going to add 1 to our power. So we're going to increase our power from negative 2 up to negative 1. And then we would divide by our new power. Dividing by negative 1 just makes it negative. Okay, so then once we've integrated, the dy is going to fall off. And then we need to make sure to add some constant plus c. I'll just call it c1. Because when we integrate over on the right side, we're going to do something similar. Okay, so now looking at the right side of our equation here, excuse me, we have a dx in this case. So that tells us on the right side of our equation only, we are integrating this function, x, with respect to x. So x is the only thing, the only letter over on this right side of our equation. And the dx tells us that we get to treat x as our variable and integrate with respect to x. So that tells us, again, just like kind of the situation we had over on the left side of our equation, when we integrate the right side, the integral should behave exactly the way we hope it would. We can just use pretty standard integration techniques to integrate this function. Now the integral of just x, we again can integrate just using the power rule. We don't have to do any changes to that function in order to use the power rule like we had to do over here. So I'm just going to kind of copy that right down here. And then let's go ahead and integrate it. So basically having x is the same as having x to the first power. So power rule says we can raise our power by 1, add 1 to our power. 1 plus 1 is 2. And then divide by our new power, which is the same as multiplying by the reciprocal of our new power. So multiplying by 1/2 would be the same as dividing by 2. So we can say 1/2 x squared. And then again, the dx is going to fall off, and we're just going to add in some unknown constant, which we will call C2. So notice we have some unknown constant C1 and some unknown constant C2. What we need to do now, the next step of solving a separable differential equation, is to basically get our y all by itself on one side of the equation, get everything else over on the other side of the equation, essentially. Depending on the context or what you need to use it for, there could be situations where this is actually sufficient, like we really don't need to go further at this point. But let's go ahead and just get y all by itself, just because that's a little bit more convenient in most situations to have it that way. So what we can do first is we can move this unknown constant C1 over to the other side of the equation. Whoops. So we're going to minus C1 from both sides. So that's going to leave us with minus y to the negative 1 equals 1/2 x squared. And then we're going to have C2 minus C1. C1 and C2 are both unknown constants. We don't know what they are, but we do know that if you add two constants together, that's just going to give you some other constant. So this is, instead of writing C1 minus or C2 minus C1, let's just kind of consolidate those two unknown constants into a brand new unknown constant, which we will call C3. Okay. So just kind of something to keep in mind here. Basically, we've kind of arbitrarily decided we're going to use a new constant C3, which is the same as C2 minus C1. Okay. That's not too important because typically you're not going to need to know what each of these constants individually are. But later on, if it were an initial condition problem, we would need to solve for whatever kind of unknown constant we have at the end, basically. Okay. So then what we can do is multiply both sides by -1 in order to cancel out this negative here. So we get y to the -1 equals -1/2 x squared. And then what we can do here, we can either say minus C4, or just to keep it easy, having a plus C, we can introduce a new unknown constant C4, which kind of like we did in the prior step, C4 is basically just negative C3. But again, that doesn't really matter. We don't really need to keep track of this over here. That's just kind of me pointing out that we're introducing new arbitrary unknown constants. So we have this new one so that we can keep it as just like plus C, basically. Just keeps it kind of simple. Okay. So then keep in mind that y to the -1 is actually the same as 1 over y. So what we basically can do is basically write, well, there's kind of a couple ways to think of it, but the kind of shortcut way is we can actually raise both sides to the -1 power, essentially flipping both sides of the equation over the fraction, leaving us with y equals 1 over -1/2 x squared plus C4. Okay, so now this is a perfectly good place to basically say that we've reached our solution. If we had an initial condition, we would have to figure out what this C4 is here. But in this case, we don't have an initial condition, so we really don't have to worry about it. So this would be our final answer. If you are getting some value out of this video, do me a favor and hit that like button down below. It's a huge help to my channel. But let's keep on rolling. I'm not seeing any questions in the live chat. As always, if you do have questions in these live streams along the way, just throw them in the live chat. If you're not watching this live and you have come a little later, go ahead and throw your questions in the comments. I'll do my best. I always do my best to answer any comments on all my videos as I can. Sometimes I miss some or can't answer all of them, but I do my best. So if you have some questions, throw it in the comments. I'll see what I can do to help you out. All right, so we have one more example here that we're going to go over. So this is an initial value problem. Basically, we do actually have an initial condition that comes along with this separable differential equation. So we are going to have to solve for our unknown constant at the end, unlike the prior example that we did. But again, the first thing you want to think about is what form is this differential equation in? Is it already in the separable differential equation form? Or if not, can we get it into that form? Well, in this case, we actually do already have one of the separable differential equation forms, which is if we have some function of x divided by some function of y. Okay, so we've already got it in the right form that we want, which is great. Because what this allows us to do is to move all of our y's over to the left, move all our x's over to the right by just multiplying both sides by dx, and then multiplying both sides by y, leaving us with the dx is canceling and the y is canceling over here, giving us y dy equals x dx. Great. So we've got our variables separated. That was pretty simple in this case. Of course, they won't always be that simple, but in this case, it wasn't too bad, I hope. If it was, leave a question in the comments. I'd love to hear any questions you have. If it's making sense so far, drop a comment down below that says, got it so far, so I know you're following along. Okay, so then once we've separated our x's and our y's, we can throw on an integral to both sides of our equation. Then we can just integrate the left side and the right side. Similar to the last example we did, y to the 1, or y is the same as y to the 1, which we can then just use the power rule to integrate. So we would keep our base y as y, add 1 to the power, so 1 plus 1 is 2, and then divide by our new power. And then we would add a plus c1, and then same thing over on the right. On the left side of our equation, we had a dy here, which means we could treat y as our variable and integrate as you would hope to be able to integrate, treating y as a variable instead of treating y as a function, like you kind of have to do with implicit differentiation problems. So it's a little bit different there. So just kind of keep that in mind as you're working with integration with different letters instead of differentiation. The dy or the dx basically indicates what letter you treat as your variable. So since we have a dx over here, on the right side of our equation, we're treating x as our variable. So again, x is the same as x to the 1. We leave our base x as x, add 1 to the power, then divide by our new power, and then add on some unknown constant, which we will call c2 in this case. Okay. Then, again, we can basically start by moving our unknown constants over to the same side of the equation. c2 minus c1, we will just call a new unknown constant c3, just to simplify things. Keep it so we only have one unknown constant to worry about later on. Everything else in our equation will remain the same. Okay. Then we can multiply both sides of our equation by 2. The 2's will cancel there, leaving us with y squared equals the 2 times this 2 here, or the 2 divided by this 2 here. When we distribute this into our parentheses here, this 2 is going to cancel with that one, leaving us with just x squared. And then we're going to have basically 2 times c3, which a constant 2 times a constant c3 is just going to create a new unknown constant, which we will call c4. And then we can just take the positive and negative square root of both sides of our equation. Keep in mind, whenever you're taking the square root like this to solve for a variable, you need to take the positive and negative square root. But that squared and square root will cancel, leaving us with y equals the positive and negative square root of x squared plus some unknown constant called C4. Okay, so now we need to deal with our initial condition. We're not done yet. If you are getting some value out of this so far, hit that like button down below and that subscribe and bell icon while you're down there too. We can keep crushing it all term long in calculus together. Okay, so our initial condition, let's deal with that. So first of all, this is the part of the problem that we were given that is our initial condition. It tells us that y of 0 is -3, okay? I'm just going to write that down here. Y of 0 is -3. What does that mean? Well, it means that when you plug 0 into our function y, we get out -3. So essentially, since we know that our function y here is a function of x, when we're plugging 0 into that, that means we're plugging 0 in for x. So basically, when x is 0, we know that our output, which is y, since y is our function, our output variable is y, our output is -3. So y is -3. When x is 0, y is -3. That's what this initial condition tells us. So what we can do is plug in these two things into this equation here and solve for C4. So when y is -3, x is 0. Okay, so then we've gotten this down to a position where we basically just have a plus C4, plus our unknown constant. So let me actually, real quick here before we carry on, just jot down what we had here was y equals plus or minus. Actually, let me write it off to the side here, sorry. Okay, so basically this is a general solution to our differential equation, not accounting for our initial condition. Accounting for our initial condition should give us C4. So I'll just write this general solution off to the side, and then we can kind of proceed with solving for this. Okay, so whoa. Okay, goodness. Bunch of random buttons got clicked there. Okay, so how do we get C4 all by itself? That's really what we're trying to do here. Well, to cancel out the squared or the square root, we have to square both sides. So that's going to give us basically canceling out the square root. It also basically cancels out the positive or negative because everything squared is going to be a positive number. So it doesn't really matter if this is negative or positive. The squared is going to cancel that out anyway. So we're going to get -3 squared is +9 equals 0 squared plus C4. Okay, 0 squared is 0. So this is just 9, not G. 9 equals C4. So C4 is 9. We can go back to our general solution of our differential equation and replace C4 with 9. So now this is going to be the particular solution to the initial value problem given here. dy dx equals x over y, where y of 0 is -3. So if that made sense, just leave a comment down below saying you understood all that. I'm not seeing any questions in the live chat, and that is everything I had prepared for you guys here today. So if you did get some value out of this video, do me a favor and hit that like button down below. Hit that subscribe button, bell icon too, so we can keep crushing it all term long together. And I'll see you next time, next Monday night.